are up. And so, not to take any more time, I would like to ask Dr. Buchanan to come up and say a few words as Steve's co-mentor.
Yeah, Steve, it's a real pleasure to be part of the introduction for Steve. Steve, when I first met him, I knew that I wanted to work with him. He was ambitious, he was energetic, he was bright, and he was very creative. And I think this exemplifies how successful he was as a graduate student and how successful he's going to be as a research scientist. But I'd like to comment that Steve has an impeccable taste for sweaters. I mean, the very first time that we had a joint party, which was a Christmas party, Steve showed up with a beautiful, highly colored, interesting sweater that actually lit up. And so Steve, actually, looking forward to your talk. I think George would be proud that we selected you, and it's your floor.
Okay. You gonna do the diploma or the plaque?
I'd like to invite the family to come up as well.
Okay. Okay. Got it.
Get the whole thing.
Yeah.
Kind of gather in front of the table there, yeah.
Do I need to be like in the center or what's going on?
You right there.
Okay.
Yeah.
You're tall, but
Oh, you big fella, I can't.
There we go. We'll do that. That'll work.
Okay, everybody, right here at me.
okay, oh, right.
Big smile. One more.
Oh,
All right. Thank you. Thank you.
congratulations.
Thank you. Thank you. Okay. Can everyone hear me all right? Okay, good. I'm going to try to keep it to 45 minutes. That's the goal today. I really, really appreciate winning the award. I really appreciate the mentorship that Bob and Craig both gave to me, and their very nice things they had to say about me. I like to tell this story because of the way that Craig is. So about 2, maybe 3 years ago, Craig invited us all over to play Mahjong. And in his basement, he looks over at me and he says, "Steve, you've got very good research, but it's all going to come down to how you write it. And I really, really want you to win the PAC Award." So here I am giving the talk after winning the PAC Award. So I guess mission accomplished, right? So anyways, all right, so my talk today is going to be about the CO2 reduction reaction from homogeneous to heterogeneous. And my thought here was to start with the work that I did here at the University of Louisville and then move on to the work that I'm doing at Princeton currently. And so I think this is a nice little through thread to kind of do that. So real quickly, just a quick outline of what we're going to talk about. So on the left here, this is the TOC image for that paper that I had here. We're going to talk about the CO2 reduction of zinc DMTH and all of the fun stuff that goes along with it. And then eventually we're going to talk about my nickel-enhanced chromium-gallium system that can turn CO2 into butanol. So that's what we're going to talk about. So why do we need to do this kind of research? Well, everyone knows that climate change is a problem, okay? And we have a very large need for alternative fuels, right? And that's resulted mainly due to the fact that our homeostasis has been disrupted by us just burning fossil fuels, right? And the EIA estimates that we're going to need a lot more energy because as we continue to just build up things, right, across the world, especially in the non-developed portions of the world, they still are going to draw energy, right? And so our CO2 emissions are going to get even worse as things go on. So we need alternative energy sources to be able to combat climate change. So one of these ideas that they have to kind of meet these goals is through this idea called leapfrogging. All right. So the whole concept of leapfrogging is you just skip the entirety of where we're currently at, right? But that needs considerable investment to do, okay? So just in Africa alone, you would need $70 billion a year to leapfrog where we're at, just to meet these goals, right? But we currently are only investing $381 billion over that time frame. So we have a $44.6 billion shortfall per year if we're trying to get just Africa to leapfrog, right? Don't even think about Asia or anything else, right? So that's a huge problem. But if you could produce fuels that currently run on our current infrastructure, then that would lessen the need to spend all this money trying to go past, right? So that can help. So what I want to look at is some various products of the carbon dioxide reduction reaction and where their references in towards gasoline. So you've got formic acid as the most common CO2 reduction product. And as you can see, it's down here in this bottom left corner. You got the volumetric energy density and the gravimetric energy density. But what I want to point out is that 1-butanol is really close to gasoline, right? So if you could make butanol from CO2, you could skip the leapfrogging, right? And you can just pour butanol into your car engine and it'll work. So that's another beautiful process that you could do, right? And you could just send old cars over to Africa. That is currently happening, and we don't need to leapfrog in that regard. All right? So when we talk about CO2 reduction, all right, it's actually pretty difficult to just put an electron into a CO2, right? So put an electron into carbon dioxide, you need 1.9 volts to be able to put that there. But the minute you start throwing some protons onto it, now all of a sudden, you don't need a ton of energy to do that, right? So why don't we just, put protons and electrons and reduce it, right? The problem with CO2 doing that is CO2 is a linear molecule, right? And if you want to do things to a linear molecule, you need to kink it, right? You need to turn it into something else. So we use a nucleophile to kink it to give our bent conformation. And then you can use an electrophile like a proton and add it there. And then you can start doing transformations to the CO2. So that's the key takeaway. So we need nucleophiles that can kink the CO2 to get there energetically. All right, so now let's just focus directly on the work I had done previously using zinc DMTH. So homogeneous electrocatalysis, you usually can only do 2 electron processes, right? And the reason for that is it's very difficult to get 4, 6, 8 electrons through an entire catalyst, right? So that's very, very difficult. So usually you make formate or CO as a product, all right? And the way you do that traditionally is you take your complex, you reduce it, all right? And if you protonate it and reduce it again, you make a metal hydride, which can attack a CO2, and you make a formate, right? Conversely, you could, after you reduce it, you combine a CO2 and a proton, and then a proton and an electron, doesn't really matter which order they come in, gives you a metal CO-bound species, which then leaves as CO, okay? So we asked ourselves, what if you did this first step as a CO2, right, instead of reducing? And to do that, we need frustrated Lewis pairs and metal ligand cooperativity. So a Lewis pair is very straightforward. You take a Lewis acid and a Lewis base. The lone pair of electrons on the base creates an adduct with the acid, and ta-da, you've got a new compound, right? However, if you put bulky constituents around the base and the acid, they can never actually make an adduct. So they can never really bind together. So you trap a pair of electrons between the two, okay? And if you trap that pair of electrons there, you can then start activating small molecules with those lone pair of electrons, all right? And while if you had frustrated Lewis pairs traditionally is one big molecule, one other big molecule. But if you put them in the same compound together, you get this process called metal ligand cooperativity, okay? And it has a ton of different definitions, but we're going to focus mostly on the fact that both the metal and ligand are going to participate in bond cleavage or bond formation steps, okay? So, zinc DMTH is a real straightforward synthesis. You can make the ligand for under $3 a gram. I'm pretty sure that's still true. And you don't have to do any crazy Schlink chemistry to get it to happen. So it's really, really inexpensive. The most expensive part of that entire process is paying a grad student to do it, okay? So, all right. You make the ligand, you can reflux it with zinc acetate, and you can make this metal, the zinc complex. However, you do get a little bit of protonated acetate left over as an impurity. So to remove that, you use sodium hydroxide to finish getting you to just this complex here. Okay? And zinc DMTH employs metal ligand cooperativity, and it's kind of like a frustrated Lewis pair, all right? So you've got, if you look at this nitrogen here, it's got only 2 bonds, right? And a lot of chemists will sit there and say, that's not right. Nitrogen needs to have 3 bonds, right? And it really doesn't have 3 bonds, and you can tell that from the crystal structure. And that's right next to, in space, this Lewis acidic zinc. So you've got a Lewis acid and a Lewis base next to each other in space, but they can never connect, all right, because of the constraints of the ligand. So that gives you a nice little cavity to do frustrated Lewis pair-like chemistry, okay? So what I want to do is give you an idea of how quickly and how much that zinc DMTH really reacts with CO2. So this is in real time, okay? This actual reaction right here. So it starts off as this bright orange, and as you bubble CO2 into it, in just that amount of time, it turns yellow. All right, so that makes things real easy, right? So you know a chemical reaction happened. It was started orange, it turned yellow, right? So we could then track how much CO2 is bound based upon the UV, right? Because, oh, look, it's orange, and now it's yellow, right? So I take the UV, I can tell, oh, how much CO2 is bound, right? Because, oh, is it partly yellow? Is it partly orange, right? So if you look at this trace here, this orange trace, you have a peak here at about 500 nanometers, okay? And if you bubble it with CO2, it's not there, right? So if you take Beer's law, A equals EBC, and you know the concentration of your CO2, you know the concentration of your zinc DMTH, you can find the equilibrium constant, which is 6.9 times 10 to the third, all right? Additionally, if you notice, hey, look, we're working at 400 ppm of CO2. We know that we're at 418 ppm of CO2 in the air. So could we just pump air into it and will it bind the CO2 out of the air? The answer is yes. All right? So you can just pump CO2 into it, or you can pump air into it. It'll bind the CO2 out of the air selectively. All right? So what is this CO2 bound structure? We thought about this for about a year and a half. And I remember when I finally grew a crystal of this, right, and Mark had solved this crystal, Craig comes down and he has the look of utter shock on his face. He's like, I can't believe it. I guess it is the CO2 bound. It is the CO2 bound crystal. And then that same day he said, hey, you're going to completely change your ORP now. So your complete ORP is gone. And if you take a crystal of this and take the IR of it, you can confirm that it has a methyl carbonate based upon the peaks that I have labeled here. All right. Additionally, Whether or not this is a methanol bound or a methyl carbonate bound, this N3, N4, and this N4, C4 bond distance doesn't really change, right? And so that again indicates that this is an sp3 hybridized nitrogen with 2 bonds in the initial structure, right? Whereas now it's protonated here in this crystal structure, okay? With 3 bonds. Okay? So if we're doing some CO2 capture, we can track it electrochemically, right? Is it first order or is it second order? We don't know, right? So if you do this electrochemically, the black trace is zinc DMTH, and the blue dotted line is when you bubble CO2 into the solution. And whether or not you pick the first peak or the second peak, it is first order with respect to catalyst. That means only one catalyst is responsible for CO2 binding, right? You don't need a second catalyst going and deprotonating or whatever. You just need one catalyst, okay? So if I take that methyl carbonate, I could react it with a hydride, right? So the easiest hydride that you usually have in your lab is sodium borohydride. And we reacted it with sodium borohydride, and as you can see, we get a big formate peak that integrates to 166, okay? But that hydride's also just going to react with CO2 in solution, and you can see that it still has 62, but it's still a massive increase, right, in overall formate production, all right? And electrochemically, we know that platinum makes hydrides, right? So why don't we use some platinum? And when you use a platinum electrode, again, you get formic acid as a product. So that's really important, right? If you use a hydride, you can make formate using this complex, right? Can zinc DMTH be the hydride itself, right? And we do the CO, all right, so here's the CV. The black trace is the zinc DMTH. You bubble it with CO2, oh look, I get a little bit of turnover for CO2 reduction to formate, right? So I get a little bit of turnover, but I get also that new peak, and that new peak is 450 millivolts, all right? So that tells you that is based on a protonated species, okay? Because it's a 450 millivolt shift, all right? You add just a little bit of acid, acetic acid, right? So we put in 10 micromolar acetic acid, you get another pre-peak indicating you have a diprotonated species, right? You still have some that are not diprotonated, and that turns over to make formate right here. And you can calculate the turnover frequency as 73 per second with a very large overpotential, all right? So if you take that and you do a bulk electrolysis experiment, you get formate as a product, and whether or not you use methanol or acetonitrile methanol or air as your CO2 source or platinum, you still create formate at pretty good yields, all right? And over here on the right, what's interesting about that is if you look at the small, at 8.3 millimolar acetic acid, you get the optimal amount of formate production. And the reason for that is the more acetic acid you add to the solution, the more you disrupt the CO2 capture in the first place. So it can never keep turning over, okay? So mechanistically, what's happening? So you've got your zinc DMTH right here where it's got an axial bound methanol. That proton ends up on that hydrazino-nitrogen, okay? And we do not know if that's through a proton shuttling effect or what fully is going on there, but we know the proton ends up here. CO2 can insert to make the methyl carbonate. We've got the crystal structure of that guy, right? A hydride then attacks our methyl carbonate right here, and you make a formate. And methanol then leaves, right, by deprotonating that hydrazino-nitrogen. Now you've got a negatively charged complex that's not going to want to keep the formate there, so it releases the formate, rebinds the methanol, and we're back to starter. Okay? All right, so now we'll move on to the work that I was doing at Princeton, all right, where we're using the nickel-enhanced chromium-gallium system to make 1-butanol. All right, So there's been a lot of work on heterogeneous catalyst for CO2 reduction, okay? And this is a table that was all done by Horry a long, long time ago. And the key point here is you got a ton of different metals that just make hydrogen. The majority make formate, a few make CO, but only copper can make hydrocarbons, all right? And that's why there's so much work done in the copper field, okay? But this is only for single metals. What is interesting is if you take two of these metals and alloy them together, okay? And so if you alloy copper and zinc together, for example, you can make ethylene. Or if you alloy copper and palladium, you can make ethylene and ethanol. Or nickel and aluminum. None of those do CO2 reduction, right? But you do that, you make one propanol, all right? Or you take nickel and gallium, and you can make ethane, all right? And then there's one other class of compounds that's really, really important here is the metal phosphides, all right? And these have been done by Dismukes to make 2,3-furandiol. But copper phosphide has been shown to make 1-butanol, but only at 3.8% Faradaic efficiency. So you make a very small amount of 1-butanol here. Okay? So I came into the Beckersley lab, and we had been working on this chromium-gallium system, okay? And a former lab member put it together, and you make oxalate in water as your product, right? So you can precipitate it out, gravimetrically weigh or figure out how much oxalate you've made, okay? And pretty darn good yields, like 60% yield of oxalate. That's a lot. However, there were some experimental flaws. For starters, use an alligator clip to connect your glassy carbon slide into your solution. And that's usually made out of steel, all right? And they use steel cannulas to equalize the pressure within the cell. And what we found out is the components of steel are important to make the oxalate, okay? So you need a little bit of that steel to make the oxalate in these high yields. So I sat there and said, how do we get rid of the contamination, all right? And we changed our design to where we take a nichrome wire and epoxy it in a piece of glass tubing. And then we put a little bit of mercury in there, and we make our electrode on a glassy carbon electrode, and we heat shrink it in place. So you get a very, very precise area of an electrode. You get a very, very precise, no contaminants whatsoever. And these work really well. They're stable for up to 4 weeks. So you can just, run it as many times as you want over 4 weeks. So anyways, so we were doing these testing, trying to figure out what components of stainless steel go and generate oxalate. And our standard cleaning procedure was, hey, take it and put it in HCl, and then sand and polish it, right? So here are your typical components of stainless steel, and is it soluble in HCl? Iron, chromium, manganese, copper, those are all soluble in HCl. But if you go up to your lab right now and take a hunk of nickel and stick it into HCl, you're not going to dissolve a whole lot of it, all right? So we got really lucky, all right? So by having that little bit of nickel on the surface, we get this NMR that you see here. And so you've got formate here, methanol, a metal acetate, acetone, and then some 4-carbon product potentially, right, that we had no clue what the heck that was, all right? And if you go and you look at your NMR impurity sheet, you'd say, oh, butanol, that should be at 3.6, not 3.19, you right? So we were like, okay, I have no clue what's going on. We integrate this. This is a 2 to 2 to 2 to 3. So Now I'm already thinking, okay, they have to be part of the same compound, right? And so I thought back to when I was in grad school, and I was like, oh, GB taught me a lot about NMRs. And he said, hey, and I hear the voice in my head from GB saying, why don't you take a cozy of that, right? And I took a cozy of it. And as you can see, all 4 of these peaks are correlated with each other based off the off-diagonal elements. So they have to be connected together, all right? And I'm like, okay, well, they're probably carbons, but let's just take an HSQC to be sure. And yeah, they are connected to carbons. So we have this carbon, that carbon, this carbon, and that carbon, where they're all connected. So you got a 4-carbon product, right, that has a CH3, CH2, CH2 structure. But again, this peak confounded us, right? We know where it is, so that has to be a hydroxy group bound to that, right? It has to be a CH2OH. But it's still a little bit upfield. And then I thought back that if you bind it to a metal, right, you can get it to shift upfield. And so that's how we know we have a metal-bound 1-butanol species. All right? And then we took an ESI-MS, and you get a big old peak of 239 m/z units. And we did the calculations of this species, and you have a 3-hydroxybutanol bound, a protonated water, and a 1-butanol. And it is perfectly square planar. It has a tau of 0.01. So it is square planar, right? As you would expect for a nickel-2 complex, right? So then we said, okay, how good is our electrode, right? So let's run under a bunch of different potentials at a bunch of different pHs and compare that directly to chromium, gallium, now that we've removed all the contaminants from the system. And as you can see, our optimal potentials at -148 and pH 4.1, all right? It gets worse as you go up, and we're not entirely sure why. As you raise the pH, the overall Faradaic yields go down. We are sure that as you go to 3.8, it's too acidic and you just have hydrogen evolution take over, okay? Additionally, as you go to more negative potentials, our Faradaic efficiency gets worse for CO2 reduction, and that's again because you just start making a bunch of hydrogen, okay? But as you go to lower potentials, you can actually generate more 3-hydroxybutanol, or you can generate more acetic acid. So it is very tunable just based upon what potential and what pH you want to run this at. So we did a long-term experiment where we ran it for 9 days, CO2 saturated solution, and we took a sampling at all of these data points, all right? And what we found is that eventually our formic acid, which is here in black, reaches a steady state, right? So it just makes the same amount of formic acid, which is going to give us a clue for later on mechanistically what is happening. Our methanol initially increases and starts decreasing at the same rate that acetone increases. So that could imply to us that the methanol is being incorporated into the acetone. Acetic acid as well reaches a steady state. And we make more 1-butanol as the 3-hydroxybutanol goes down. Eventually, the 1-butanol starts decreasing, and we see an increase of what we call C5 plus products. So we know that the butanols are starting to couple because you've now got an organic soup, right? They'll start to do all kinds of crazy stuff together. This black spot, we added more CO2 saturated water just to make sure that it had enough. And because it was still catalytic, right, that tells us that the electrode was still working here at day 7. All right, so now you're probably asking me, hey Steve, how are you sure that it's coming from carbon dioxide, right? How am I sure that I don't have butanol just sitting in my cell or butanol in my NMR tube, right? And so we took some radio-labeled CO2 and we put that into the solution to enhance that signal. And what we can see is if you blow up that region right here at 8.5, you get a nice triplet that you expect to see from radio-labeled formic acid. All right, so that tells us, hey, formate's definitely coming from the CO2. All right, then if you look directly at this region with the acetone and the acetic acid, again, you get those triplets telling you, hey, that acetone and that acetic acid, those are definitely coming from CO2. All right. Finally, we said, hey, let's go take a carbon NMR, right? That's the first thing your advisor would have said, right? Go take a carbon NMR of it, right? And as you can see, those same 4 peaks that I showed you in the HSQC, they're right there in my NMR. So that tells me, hey, that butanol is coming from CO2. So that's pretty cool, right? And if you do a overall carbon yield, it's about a 30% carbon yield. So the amount of carbon that you put in, you get about 30% back out as product. All right? Now, if you take, we sat there and said, okay, we know nickel's important, right? Nickel's got to be important for this overall reaction. Can we do different ways to make this same catalyst, and will it work to also make 1-butanol, right? Because if I go by, like, say, a Watts bath, then I'm electroplating nickel, right? I can reduce the amount of nickel that's on my surface by taking, after electroplating, I can put it in HCl, right? And I can abrase it with sanding and polishing it, right? Or maybe I could use some nanoparticles, right? Or what if I put some nickel nitrate down on the surface, reduce it, give me a nice nickel layer, and then drop cast the chromium gallium on top of that, right? And here are the results of all of these electrodes. I know it's a giant table and yeah, it's crazy. Anyways, what is important to note is the more nickel that is touching the solution, the more hydrogen you make, okay? So the more nickel that's touching the solution, you're just going to make more hydrogen because you make a hydride, hydride's going to turn over to make hydrogen. All right? Additionally, if you add more nickel like we had in route 2, route 4, and route 6, right, you see a lot of 3-hydroxybutanol as a product, right? And if you remember, that was the aldehyde that I showed you earlier on the mass spec. All right? And the other thing that's cool is that chromium gallium is really, really efficient for making acetic acid. So if you just want to make acetic acid, use a chromium gallium oxide electrode. All right? So we did a bunch of mechanistic studies. The first study I said is, hey, we didn't see any CO as a product, so could this be going through a formate pathway? Right? So the first study you would do, take formic acid, put it in your electrochemical cell, do it under argon, right? And look, we get all of the products that we said we get. So hey, formic acid is the first step, right? You have to make your formic acid. And then we looked back at this paper by Lee, and he suggested that you make 1-butanol using acetaldehyde, all right? And if you add some acetaldehyde to your cell, in the nickel-enhanced route, you get 1-butanol. The chromium gallium, no 1-butanol. You take a coiled up piece of nickel, you get a little bit of nickel. But the minute that you subject it to a Watts bath, or you take that nickel coil and Watts bath it, so you put a specific face of nickel onto the electrode, you get a ton of butanol. So it could be face specific, or it could be concentration specific, or it could be both. We're not 100% sure of what it is. Probably both. All right? So mechanistically, we know that you generate a surface hydride based on the KIE. The KIE for our overall process is 0.93, so you know you get a hydride. The hydride attacks the CO2 and you get a bound formate. You could protonate that formate and boom, there's your formic acid. Or another surface hydride can attack it and you make formaldehyde. All right? That formaldehyde can be hydrogenated, you make methanol. Or you can take 2 of those formaldehydes, couple them together, and you end up with acetaldehyde. That can react with water, right? Your aldehyde leaves as H2 and you make acetic acid, or that aldehyde could react directly with your methanol and you make your acetone. But more importantly, if you take two of those acetaldehydes, couple them together, you get that 3-hydroxybutanal, which you can then hydrogenate, and boom, you make nickel-bound 1-butanol. So, some conclusions and future directions. Zinc DMTH, as far as my knowledge, is still the only CO2 reduction catalyst from air. And this nickel-enhanced chromium-gallium system is the first copper-free catalyst to make 1-butanol. And it's by far the most efficient, right? 64 versus 3.8, all right? And it happens through an uncommon pathway, and we're currently substituting other metals in place of nickel, and that's the future direction of that project. So I would like to acknowledge a lot of people here. First, I want to acknowledge the PAC family. Thanks again for coming. I appreciate everything and all that. I also want to thank just the General Department of Chemistry here for giving me the award and also being good people to learn from. And then I especially want to thank a lot of my U of L family, Craig, Bob, Mark, Neil, a former PAC award winner, Dr. Haddad. He's the one who really taught me everything that I know. So I really, really want to say, anyways. And then I want to thank my Princeton family. These first 5 names here are all people that work with me on this nickel enhanced system. And then Rebecca and Val work with me on my project that's funded by Oak Ridge and the NSF. So with that, I'll answer any questions.
We're being streamed live to the world via YouTube. So if you ask a question, can you speak into the microphone?
First, congratulations on winning the award, and I enjoyed listening to your talk. I have a question about the second half.
Yeah.
What do you think about the economic reality of this catalyst? I mean, you're using kind of expensive metals compared to copper. Also, selectivity is probably something you're working on, which is going to cost a lot of money to separate these different chemicals to use them as fuel. So what do you think about that?
So economically, it's actually not that bad, right? Because nickel's fairly cheap, right? Now gallium's a little expensive, but you can reuse these electrodes, right? And we've actually gotten it such that we can make our overall 1-butanol yields high enough to actually separate directly from the overall system. So you make a actual layer with your solution. So you can just add acid, boom, and then you could just scrape it right off, or you could take a pipette and pull it right off. So the separation is probably a lot easier. The problem is really once we start moving from glassy carbon onto maybe HOPG or vitreous carbon, trying to make sure that it still works when we move in that direction.
Okay, thank you.
Steve, you focused on the applications of these materials for creating fuels.
Yes.
Do they have any application in carbon or CO2 removal?
They do not bind CO2. Only the zinc DMTH, right, binds CO2 directly from air. So you could couple essentially zinc DMTH to these nickel-enhanced chromium-gallium systems, right, and pull the CO2 out of the air, use the nickel-enhanced chromium-gallium to convert it, right? So you have both sides of that coin.
I think I had a question from Dr. Muller.
Nice talk and interesting work, Steve. I expected nothing less. Can you go back to the kinetic isotope effect?
Which one?
Well, that's the one you talked about.
Yeah.
Explicitly. So I assume that was on carbon-13.
No, we did the kinetic isotope effect doing D2O. So our entire experiments run in water, right? Millicube water. And so we then replace that proton source with D2O.
All right, how do you get an inverse effect? How do you explain the inverse isotope effect?
Well, that indicates that you have a metal hydride.
Why?
It's
That's
just,
what I'm,
it's well known throughout the literature that if you have a KIE less than 1, that you likely have a metal hydride.
so it's not on the step where that you have shown there then?
The very first step where you generate that hydride, that has to be the very first step because of the KIE being 0.93. The rate determining step, yeah.
Yeah. And I'm still confused. Well, I'll have to look into that. I'm just really surprised that you would remove a hydrogen from water anywhere and not see a primary,
Yeah.
normal effect. So, thank you.
You're welcome.
Any other questions?
So on your NMR, where you said that the carbon peak was shifted because of the metal binding,
Yes.
so are you suggesting that there's stoichiometric nickel in there, or is this in some rapid equilibrium between a metal bound and non-metal bound?
I would suggest that's probably a rapid equilibrium, right, because of the concentrations. But that ESI really tells us that this has to exist based on the ESI. So we have to have specifically that complex hanging out in solution.
Or at least in the gas phase?
Or at least in the gas phase, yeah.
And a second question, can you talk a little bit about what your current density is for your electrodes?
So yeah, our current densities, give me a second, I've already included those so you can see. These are the SEMs, there you go. All right, so we did a bunch of linear sweep voltammetries. These currents are in milliamps. I've asked Stephanie to put these in per centimeter squared. So as you can see, the root 1 doesn't have a ton of current density, right? So, right, our overall current density that 0.9 is about 0.72 milliamperes per square centimeter, and then we get up to about 2 to 3 milliamperes per square centimeter.
Nice talk, Steve. You want to hypothesize what you would expect when you move to cobalt
Instead of what?
instead of nickel?
That I don't know. I would guess it'd make it a better hydrogenator, but maybe not a better cross coupler, right? So you might be better at hydrogenating that, but so you may end up, right, stuck kind of here. And so we're actually not looking at cobalt, but we're actually looking at rhodium for that exact reason.
Great talk, Steve. I was just going to ask, why is the zinc complex the only one that can reduce CO2 out of air?
Usually oxygen poisons catalysts, right? So if you go and you just pump air into it, right, you're 20% oxygen, 21% oxygen. So that usually, like, let's say you have an iron catalyst, right? You automatically oxidize your iron catalyst, right? And so a lot of them have to recover over that hill of being reoxidized. And so, yeah. Yeah, not solid state. Yeah, it's the only homogeneous catalyst to do that.
Yeah. So yeah. Thanks, Steve. I'm not a chemist. I'm not even sure if my dad was a chemist, to be honest with you. Yeah, I think he was really a biochemist, but he seemed to fit in well here. So I won't question that too much. But I'm not a chemist, so I wasn't really able to follow a lot of it, but I really appreciated there was a story in your talk that we were kind of able to follow, I think, to some extent. So that was kind of, I could tell you were a teacher at one point, as you were able to work that in amid something that is, highly specialized. But I guess I have a question, and maybe you won't really be able to answer it for somebody who has my level of understanding of this, but I was trying to figure out, like, obviously this is an important problem you're working on. There must be other people who are trying to do this kind of thing, and it's a problem that we've known about for a long time. So I was trying to understand like what the breakthrough, not your breakthrough, but a breakthrough in the science that might have happened that made your work possible. And I was just looking to see if there was like one thing, one discovery that you were able to sort of stand on the shoulders of, or if it was just kind of just this trial and error throughout.
Yeah. So the zinc DMTH stuff, we actually got a little lucky on that. So previous to doing the zinc DMTH, Andrew, who won the PAC award in 17, was working on ATSM, which is, if you look at if I go back to it. So if you look at this complex, if you split it right here, right?
Yeah.
If you take this and did a mirror image of it, that's that complex. So, right, so you have this guy,
Oh, yeah. Okay.
right? So it's the mirror image of that. So one of the things we thought about is, well, what if you put a pyridine here? Could that be an electron reservoir to help us with hydrogen evolution? And then we found that, hey, this stuff is an orange solid. You put it in solution, it turns yellow. And what we found is it was actually reacting with the air to turn it to that yellow. And so we got really lucky in that regard.
Okay, so that was the sort of the moment when you were, okay, all right, thanks.
Yeah.
Appreciate it.
Okay, any other questions?
Yeah.
Okay, well, if there are no more questions, thank you for coming this year, and congratulations to Steve. Okay, and enjoy your evening.